Hi everyone, here we are on chapter 28, and chapter 28 is on nuclear chemistry. Nuclear reactions take place in the nucleus, all right? So which two subatomic particles do we find in the nucleus? So protons, electrons, or neutrons? So which two out of those three are actually found in the nucleus? Do you remember? We can find the protons and the neutrons, okay? So the protons and the neutrons are found in the nucleus, and that's what we're going to look at when we're talking about the stability of the atom. Now, your nuclear reactions are very different than the chemical reactions that we have been talking about. If you recall, the chemical reactions, we take a look at their stability based on how many electrons they have. Remember that they want to either gain or lose electrons to be stable, like one of the noble gases. Now, your nuclear reactions are a little different, okay? What we are going to do is compare the ratio between the protons and the neutrons to determine the stability of the atom, okay? So then that means that if the ratio of protons to neutrons is too large or too small, then therefore it could be an unstable nucleus. And we call that a radioisotope. Okay, so an unstable nucleus is called a radioisotope. Your nuclear reactions are also not affected by pressure, temperature, or catalysts. Now we are going to talk about radioactivity. Okay, radioactivity. Once again, something is radioactive because the nucleus is unstable. All right, so these are things that you need to know. All right, the stability of the nucleus depends on the ratio of neutrons to protons. So if there are too many or few neutrons relative to the number of protons, that's how it would be classified as being unstable and then therefore radioactive. Okay, now we're going to talk about radioactive decay. So this is what happens over time. The nucleus is going to decay over time. Eventually, it'll decay into a stable nucleus, okay? So obviously, when it decays, it will emit radiation, okay? It will emit radiation. And it is important to know that the unstable radioisotopes will be transformed, okay, into something that is stable. So when a nucleus is stable, it is not radioactive, and therefore it would actually be a different element, okay? It will be a different element. All right, there are three types of radiation that you will need to be familiar with. So the alpha, it's drawn on your PowerPoint notes correctly, just that this program doesn't like these Greek letters. So alpha, it looks like a letter, kind of like a cursive A when it's in the typed font, but it's actually like the sideways, like a sideways little fish there, okay? So that is the symbol for alpha. Now, alpha radiation could be stopped by a sheet of paper. It can even be stopped by like the top layer of your skin, like the dead skin cells. So that is what can stop alpha. So you need to know what can stop alpha. You also need to know the charge on it, okay? So alpha has a positive charge and it gives off a helium atom. So then on your notes, it's written correctly. The 4 should be on top, not right there. Okay, so then the helium atom, 4 on the top, 2 on the bottom, and this is how we can identify what type of radiation it will be. So here's an example, uranium, okay? If you remember, the bottom number here is the atomic number. So that's the number that goes in order on the periodic table, and that tells us the number of protons. The number on top is the mass, okay? Now just remember that the mass here may not necessarily be the mass that you find on the periodic table because it could be an isotope, okay? It could be an isotope. And if you recall, isotopes are where the neutrons vary, and that's how we get different masses. Okay, So then in this particular example, since it is alpha radiation, you'll notice right there that an alpha particle is being released, okay? It will release a helium atom, okay? Now in the process, it's going to produce thorium, okay? Now we know that it will produce thorium because of the law of conservation. On each side of the arrow, we have to make sure the numbers that are on top and bottom here add up on both sides of the arrow, okay? So then if it's 92 on the bottom and it releases a helium atom, then that's why it's 90 on the bottom here, which corresponds to thorium. So if it's 238 on top, so and this is already 4, so then therefore the mass of the thorium must be 234. Okay, and once again, it could be an isotope of thorium, so that mass may not necessarily match with what you see on the periodic table. Okay, so that's alpha. Now beta radiation, beta is written as like a letter B, but it has like a long tail. So beta looks like this. Oops, I usually start from the bottom and then go up. Beta radiation will release an electron, okay? It releases an electron, and therefore it has a negative charge because electrons are negative, okay? And you could actually use a sheet of aluminum to stop beta, okay? So the electron, notice here, is -1 on the bottom and then 0 on top because the electron doesn't have mass, or the mass is so insignificant. So once again, we just do the math so that the numbers on bottom and top here will add up on both sides of the arrow. So that's why this was 91, because 91 minus 1 equals 90. And then 234 on top, because 234 plus 0 equals 234. Now the last type of radiation that you need to be familiar with is gamma. Gamma, it looks like a letter Y when it's in the typed font, but it's actually drawn, oops, pen, it's actually drawn like that, like an upside down fish, okay? Now gamma, out of all of them, is the strongest radiation. That's why we need the minimum of lead to stop it, okay? Gamma has no charge and no mass. So if you notice here, that's why there's a 0 on top and a 0 on bottom. This is just a coefficient too, to let you know that in this particular reaction, that it releases twice as much gamma rays, okay? Now notice here that we also have a helium atom being released, and so it also has alpha. Many times you will see gamma being accompanied with either alpha or beta radiation, okay? And that's also so that the nucleus can change. Since it's only 0 on top and 0 on bottom here, then therefore we know through radioactive decay, it does transform into a new nucleus, okay? So same idea, numbers on the bottom have to add up on both sides. So 2 and 90, and that's just a 0, so it adds up to 92. 238 on top, 4 and 234, and that's just plus 0. So numbers on top and bottom add up. Okay, so we just went over alpha, beta, and gamma. Out of all of them, alpha is the weakest because it only needs a sheet of paper to stop it. Gamma is the strongest. We need lead or even thick layers of concrete could also stop gamma radiation. Okay, now the reason why alpha is the weakest type of radiation is because out of all of them, it is the heaviest particle, okay, or it's the biggest particle. So bigger particles travel slower. Therefore, alpha radiation is not as penetrating as gamma radiation that doesn't have any mass at all, okay? So make sure you understand that concept also. All right, now Rutherford, who we have talked about many times before, remember he is the one that did the gold foil experiment and discovered the nucleus and stuff. Well, he also discovered the charges on alpha, beta, and gamma. He did a lot of studies on radioactivity, okay? So let me just kind of draw a picture here. What he did was he had a lead box and he had like a piece of thorium, okay? He used uranium and thorium inside this lead box, and what he did was he put this through a magnetic field. So a magnetic field means that it has a positive plate and it has a negative plate, okay? So what he discovered was the radiation from the uranium and thorium, when it was put through this magnetic field, he noticed that there were some rays that passed straight through, and some of the rays bent up towards the positive plate, and then some of the rays were bent down towards the negative plate, okay? Now, which particle do you think was attracted to the positive plate? That would be beta, okay? Because beta is negative and opposites attract. Therefore, it is alpha. Let me draw alpha better. Alpha was attracted to the negative plate. Since alpha has a positive charge, it is attracted to the negative plate. And then gamma, since it has no charge, it's neutral, it passed straight through. Okay, we are going to talk more about nuclear stability, okay? Nuclear stability. Once again, remember, the stability of the nucleus depends on the ratio between protons and neutrons, okay? If it's stable, if it's already stable, it doesn't need to decay or transform into something more stable. It's already stable, okay? It's not necessarily going to change over time. It is only the radioactive or the unstable nuclei that will actually transform over time, okay? Look, there are 1,500 known nuclei, so that means including all of the isotopes. And out of that 1,500, only 264 of them are stable. So the majority of the nuclei that are found are actually radioactive, okay, and very unstable. Now here is a graph. It's called the band of stability. So if you notice here on the bottom, okay, the number of protons are on the X and the number of neutrons here are on the Y. So when they plotted protons versus neutrons here, this straight line here, the solid straight line, that's if it was a 1-to-1 ratio between protons and neutrons, okay? Then everything in this like speckled region here, everything in this speckled region is what we call the band of stability. So when they plot the points of protons versus the neutrons, and if it falls within this band here, then it's considered to be stable, okay? If it falls outside of the band, then it's an unstable nucleus. Okay, you also need to make sure that you understand this concept of half-life, okay? Half-life, okay? So half-life is the amount of time needed for 1/2 of the atoms to decay into products, okay? And yes, in that process, as it is decaying, it will emit radiation. So here's a sample half-life problem. You will see a half-life problem on your test. All right, so assume there are 2 grams of nitrogen-13. Okay, so nitrogen-13, meaning that this is an isotope of nitrogen. So they're talking about nitrogen with a mass of 13. They want you to figure out how many grams of nitrogen-13 will exist after 3 half-lives, okay? So when we're doing a half-life problem, it's like a half of a half of a half every time, okay? So technically, we will never reach 0 if we just keep taking a half of a half of a half every time. We get pretty darn close to 0, but we don't actually hit 0, okay? So this is how you could set up the problem. I put 0 half-lives here. So this is the initial. We are starting off with 2 grams, right? Starting off with 2 grams. So initially, we have 2 grams. If 1 half-life passes, that means half of the 2 grams will remain. So half of 2 is 1. Take another half-life. Half of 1 is 0.5. Then do the third half-life. Half of 0.5 is 0.25. So after 3 half-lives, 0.25 grams of nitrogen-13 will remain, okay? So notice here, that's all we did. Took a half of a half of a half, okay? That's half-life. Half of a half of a half every time. Now, here are some common uses for some of the radioisotopes that you might already be familiar with because you might have read about these in even like history books and stuff, especially the carbon-14. Carbon-14 is what they use for carbon dating. Okay, that's what they use for carbon dating to determine how old some of the fossils are. Now, some of the radioisotopes are actually man-made, okay, artificially produced, and a lot of those we might use in nuclear medicine. Uranium-235, now look at the half-life on uranium-235, okay? That's like 4.5 billion years. And that's how we were able to discover how old our universe is based on dating rocks with the uranium. Okay, transmutation reactions. So transmutation reactions, it says right here, the conversion of an atom from one element to an atom of another element, okay? A lot of times in these transuranium reactions, you'll see them being accompanied by alpha or beta reactions, okay? Now, the majority of these transmutation reactions are actually artificially done in laboratories. In other words, they are man-made, okay? They are man-made. So, if you look at the bottom of your periodic table, the 2 rows at the bottom, the majority of those are man-made. Okay, they were discovered in labs. And so Berkeley has discovered some of these, even Stanford has discovered them. They can use what are called linear accelerators or cyclotrons. And what they do is they take these high-speed particles and bombard a nucleus with these high-speed particles, and then we have like a new nucleus. Okay, and that's how they discover these new atoms, and these are ones that are actually made in labs. You cannot find them out in nature. All right, so your transuranium elements are typically above atomic number 92. Okay, so those are usually the transuranium elements. Once again, those are the ones that are man-made, okay, made in the laboratories. All right, so that is where we are going to stop today. And then the next lecture and the last lecture for chapter 28 will be on fission and fusion. Okay? All right, see you later. Bye.